Okay, so if you remember, yeah. The amplitude ratio and what?
And phase that.
Okay, what would you like me to mention about that? So, you know, for a given, so here phi is minus omega t. So, well, let me do it in the context of this. Okay, if you recall, we've been looking at problems in the Laplace domain. And in the Laplace domain, we typically have functions that we want to invert. And the Laplace domain is typically, we've written it as a ratio, where the denominator generally comes from the left side of the equation, and the numerator tends to come from the forcing function. So the denominator tends to come from the system, and the numerator tends to come from the forcing function. And we've assumed in this class that the numerator and denominator are generally polynomials, although we may allow putting polynomials times exponentials, particularly the numerator. Maybe we're allowing exponentials in the numerator, but generally we're restricting our attention to polynomials in the numerator and denominator. And the point of the matter is, what we saw so far is that the roots of the denominator, the zeros of the denominator, end up being the alpha I that are in terms that look like exponentials. So it's the roots of the denominator and not the numerator that determine stability, because the time dependence has an exponential. It may be an exponential times sines and cosines, but sines and cosines just oscillate, exponentials grow. Now, of course, you could have t to a power times an exponential times a sine and cosine as well. But generally, it's the roots of the denominator that determine whether something is going to blow up exponentially or linearly, or as a polynomial, or decay polynomial or exponentially. But if you actually want the details of the full time-dependent solution, you also need the coefficients, and that comes from the numerator. We also introduced the transfer function, which in the Laplace domain, which was the Laplace transform of the output divided by the Laplace transform of the input. Again, in prime variables, because this is assuming that the initial condition is 0, and the whole point of prime variables is they make the initial condition of the prime variable 0. And we saw that, whereas it looked like just a cute little ratio, what we found was that this y prime over x, y prime tilde over x prime tilde, we saw that it contains a lot of information. We saw that even though the roots of the denominator tell us about the stability, we could get, if we have, that's of course useful, particularly if we have a step input or a pulse input. But if we have an oscillating input, a sine or a cosine, then as long as the system is linear, we know that the frequency of the output is also going to oscillate, is the same as the frequency of the input. That's not necessarily true if in a nonlinear system, but in a linear system it is. And the amplitude ratio, we can get directly from G tilde without even doing the inversion. And we saw that if we just take G tilde evaluated by omega, where omega is the frequency of the oscillatory input, and take the magnitude, we get the amplitude ratio. And phi, the phase lag, that is, if something's oscillating in the input, the output may not start oscillating until here, and that difference, that distance in radians, is the phase lag. I can get also directly from G tilde without inverting, as the arctangent of the imaginary of the real part of G tilde by omega, which is an amazing advantage of the Laplace of working in the Laplace domain, because the difficult part of working in the Laplace domain is doing the inversion. And we can answer many, many questions without even doing the inversion. So that's really, and instead of solving differential equations or integral equations, or integral differential equations, we're just solving algebraic equations. So that's a big advantage of Laplace, working in the Laplace domain, as long as our problems are linear or we can get away with linearizing. Obviously, in more advanced courses, not this course, but in more advanced courses, where you work with in control, where you work with nonlinear systems, then the Laplace domain is really mainly useful in the linear limit. But that's again beyond the scope of this course. which is a phrase I always hate to read when I read in the textbook, saying beyond the scope of this book. Okay, now we start now, in reference to the question, we saw that it's sometimes useful to, and actually we didn't really see the use of it, we just made plots. We made plots of the log of the amplitude ratio versus the log of omega, and log and phi versus the log of omega. We made those plots. So, for example, in a first order system, we found that, which looks like this, where t is a time constant and kp is the steady state gain. Then, and this was, we saw in a first order system that was self-regulatory. Self-regulatory meant if we bring the y to the other side of the equation, when y gets big, then it comes in as a negative and makes dy dt small. It brings down dy dt. So when y gets too big, dy dt is forced to be negative. So that's called self-regulatory. And in that case, we have the coefficient here is kp. And we found that g tilde is kp over 1 plus st. And the amplitude ratio was 1 over the square root of 1 plus omega squared t squared. And we found that phi was equal to minus omega t. And we plotted these. We plotted them for a first order system. Where this had a slope of minus 1. And this was kp here. And when we plotted the log of phi versus the log of omega, actually just phi against the log of omega, we saw that this looked something like this, where this was minus pi over 2, and this went to 0 eventually. So here we had those plots. For a second order system, so does that answer your question, or do you want to go into more detail about this?
Yeah, can you explain the negative pi over g?
Can I explain what?
How do you do negative pi over g? For the phase that?
How did I get to minus pi over 2? Because in this particular problem. Okay, so phi is the arctangent of the imaginary of the real part. And if we look at the tangent function, the tangent function looks something like this, if I plot it. Because the sine of 0 is 0, I should have gone through the origin. The sine of 0 is 0. The cosine of pi over 2 is 0. And here the sign is positive, here the sign is negative. So this goes to plus infinity, this goes to minus infinity. So as omega goes to infinity, minus omega t goes to minus infinity. As I go to minus infinity, that tells me that the arctangent, so if the tangent goes to minus infinity, the arctangent, the phi is going to minus pi over 2. And that's how I get the minus pi over 2 here. Okay. And then I went through a more detailed explanation why in the second order system it went to minus pi. And there I sort of marched through. And that you'll find on the video of that particular class. Does that answer your question? Okay. Great. So now for a second order system, we had which we saw we could put together out of two first order systems, or we can have a more general one where we let C be anything we want. And we saw this was related to the block oscillating on a spring with friction. And that's why we call C the damping, and that came from that analogy. And again, we have a Kp here because this is made out of two first order self-regulatory systems. And we found that G tilde was equal to Kp over a quadratic. And we solved for the amplitude ratio, which was Kp over the square root, which if we set C is equal to 1, just gives us Kp over 1 plus omega squared t squared, which is what we had gotten in the example earlier. And it also makes sense because it's two first order systems in series, and it's just the product of two first order systems. If I take this and another one, and I multiply each other, I'll get the square root squared, which is 1 plus omega squared t squared in the denominator. That's, of course, in the case where C is equal to 1, which corresponds to the case where I have two first order systems in series. If I let CE anything else than 1, it's a more general second-order system. That's not just 2 first-order systems in series. But when it's 2 identical first-order systems in series, then C is equal to 1, and then I just get this expression right here. At the end of the last hour, we started looking at the integrator system. And just to save myself a little board space, and this has been on before, I'm just going to erase this because this has been on the board before. Is that okay? Okay, so in the integrator system, it's not self-regulatory. Notice I left this y out. So when y gets big, nothing makes dy dt get smaller. It just depends on x prime. And since it depends on x prime, since it's not self-regulatory, there's no guarantee I go to a steady state, so I didn't put a kp here. This was only, and in fact, we'll see in 1 second what happens there. So we integrated this directly, we divided by t and integrated it, and for a step response, or step when of the thickness delta x, we saw delta x comes out, and I just get delta x over t times t. Delta x over big T times little t. So we see that this grows. The step response, instead of reaching a steady state, just grows linearly with time. And if I have a pulse response, someone takes a bucket with a volume of m and dumps it in our system, this is just becomes m times a delta. M comes out, m over t, and the integral of a delta is just 1. So I get m over t. So the pulse goes to a constant, doesn't go to 0, it goes to a non-zero constant, and the integrator goes here. And what I'd like to do is just continue with that a bit, because this is where we left off. But before I do that, now that a bunch of people are here, what I would like to do is spend 2 minutes just a little bit on generality of the class. What you notice in some of the classes is I call on people when I have something really trivial in mind, like the derivative of x squared, or something I said 5 minutes earlier, and I ask you to repeat it. Now, why do I do that? I'm doing that not to try to scare you, and not to try to be mean. Some people think that's mean. I'm doing that because for 2 reasons. On a local level, a simple level, it just makes the lecture more interactive. And interactive lectures means you end up paying attention more, and if it's interactive, then I find it, at least from my perspective, it's less dull. If it's a monologue, then it's less interesting than if you're actively participating. But the main reason I'm doing it is when you graduate and get a job in the real world, this is not the real world, this is a university. When you go into the real world and you get a job, your boss is very typically going to bring you in a room with your coworkers and ask you questions. And ask you questions to answer in front of all of your coworkers. And when your boss asks you that, it matters if you get the answer right or not. Here, it doesn't matter. What I care about is what you do on the exam. When I ask you a question in class, I really don't care if you get it right or wrong. I prefer you get it right, but 30 seconds later, I've forgotten who's gotten it right and who's gotten it wrong. So the whole point, and what I find is with many students, since you're not used to this, people, you ask them a question, how much is 2 plus 3? And something they know. Like last class I asked about the solution of a quadratic equation. Everyone in this class knows the solution of a quadratic equation. But people freeze up that if I ask them their name, they wouldn't be able to tell me. They tell me the wrong name. Now you have to get used to being asked questions and answering. If I'm asking you a question in class, I am not testing you. I am trying to make the system more interactive, and I'm trying to get you used to being called on. Because in this class, it doesn't matter if you get the answer right. But when you go at work, it will matter. So you want to get used to being asked questions and answering. And relax. It doesn't count for anything if you get it right or wrong. It's just getting you used to it. So that's my little spiel about being asked questions. You have to get used to not getting scared if I ask you how much is 2 plus 3 or what's the solution of a quadratic equation. If you're getting scared, then you won't even be able to tell me your name. And that's not going to work in the work world. It doesn't matter here, it will matter there. Okay, with that little introduction, let's get back to what we were doing. So we were looking at the integrator system, and let's do the Laplace transform. And make sure everyone has their sheet available, because we refer to it. What's the Laplace transform of the derivative? So here we have t. What's the Laplace transform of the derivative of y?
Usually s.
A little louder.
The general is s times s minus
I can't hear you.
I was going to say, generally it's s times s minus.
F tilde, yeah. So it's s, because I'm in the prime variables, these are prime variables, it's s y prime tilde. And on the right side, I get x prime tilde. Because the Laplace transform of the derivative gives me a factor of s. And g tilde of s is equal to y prime tilde over x prime tilde, which is 1 over st. So the first thing you can see is that the limit as s goes to 0 of this is infinity. So I'm not going to a steady state. I'm not necessarily going to a steady state. And this is, of course, this was first step. Okay, so let's look at the amplitude ratio, g tilde of I omega. That's the magnitude of 1 over I omega t. Well, let's see what that is. Remember, in order to get a magnitude, I need the I in the numerator, not denominator. So the way to get I in the numerator is to multiply and divide by I. And if I do that, I have I over minus omega t. So the magnitude of I is just 1. It's just 1 times the square root of minus 1. And the magnitude of this is just its size. So I have 1 over omega t. So that's g tilde of omega, of I omega. And phi is equal to the arctangent of the imaginary part over the real part. Well, the imaginary part here you can see is minus omega t, and the real part is 0. The real part is 0. So what's happening there? Well, that's the arctangent of minus infinity, and we said the arctangent of minus infinity is minus pi over 2. So now that may seem a bit abstract, so why don't we look at the solution here, at this thing. So let's say if I have a sinusoidal input, if x prime of t is a sine omega t, then let's see what y prime of t is. Is equal to a over t, the integral from 0 to t, sine omega t, dt prime. Where I put a prime in because I can't have the same variable in the as a variable of integration and in the limit. So they're different variables now. What's the integral of sine omega t? Do we have a volunteer here? This is simple calculus. 1 over omega minus cosine omega t. So this is a over omega t times minus cosine. So minus cosine, the minus I use to flip the limits, so I have 1 minus cosine omega t. Okay, so let's notice that x prime had an a. So what is y prime? Y prime is this. This is b, the coefficient. So the amplitude ratio is b over a. Is a over omega t divided by a, which is 1 over omega t. So notice, here I did it explicitly. The b over a, the amplitude ratio, I have a sine coming in, and I have a 1 minus cosine coming out, and the ratio of the coefficients is 1 over omega t, which we showed is indeed the amplitude ratio. Where is it? 1 over omega t. Moreover, what is the phase lag? So the phase lag between the sine function and 1 minus the cosine function is exactly minus pi over 2. So here you can see things that we calculated using methods we derived in class. And then in this particular case, we could just calculate it directly, and we found what these are. And notice the sine function looks like this. The cosine function starts here, but 1 minus that, so minus the cosine is here, plus 1. But it, yeah, so you have the cosine function looks like this. Minus the cosine function flips it. So let's do minus cosine. And when I add 1 to it, it just comes up, and this looks like this. This is 1 minus cosine omega t. And you can see that the peak here, this starts out, this, well, let's see where this peak, actually I didn't do it very well. No, I didn't do it right. So it actually does look like this. So this peak, which corresponds to the same place as this peak, is further over than this peak, and the difference is minus pi by 2. I didn't draw it very well, but you can check that. So this is the integrator that we've been dealing with, or that we wrote. And the big difference between the integrator and the self-correcting is that for a step function, these both go to steady states, and I have a steady state gain, whereas the integrator, since it's not self-correcting, doesn't. It grows linearly in time. When I have a step input, when I have a pulse, it gives me a constant. Remember that the self-correcting systems forgets a pulse eventually. And when we have a sinusoidal input, then we still have an oscillatory output, but the amplitude ratio and the phase lag are what we're able to determine here. Any questions on that? Now, when we were talking about self-regulatory systems, we could have a system. So this is an example of self-regulatory. So we could have a system where we have a heat exchanger here. And if we write this out, so we have a system here where we have an exothermic reactor. And we're interested in the temperature. So here we have theta in, and here we have theta. And what else would I like to write here? And here I have theta C. So I can write for the temperature here, rho V CV, d theta dt. So the accumulation is in minus out. So I've got rho times the volumetric flow rate times Cp, theta in minus theta. So that's theta in is being flowed in, theta out is flowing out. And then I also have UA times theta, so what's theta C in minus theta. So here, if theta C in is hotter than this, then I'm putting heat in. If theta C in is lower than theta, then this becomes negative, I'm taking heat out. And then I could have my reaction here. So the reaction has a reaction rate. Times minus delta H. Minus times the heat reaction. And let's see if there's any more notation I want to include in there. And this rate of reaction I can write as, how did I want to write it? The rate of reaction has a k in it, which is k0 e to the minus e over r theta times some function of the concentrations. So let's see what happens here. If this is exothermic, then delta HR is negative, so this thing is positive. And let's see what happens here. Let's notice that we can bring some of these thetas to the other side of the equation. I've got rho v CV. Actually, let's divide through by rho v CV. So I'm going to divide through by rho v CV, and I've got a d theta dt is plus little v over big V, which is 1 over tau theta. And then here I have plus UA over rho v CV times theta. And that's equal to what's left here, which is 1 over tau times, and here I'm assuming CV equals to CB. 1 over tau theta in plus UA over rho v CV times theta C in. And then I have plus K0 e to the minus E over R theta, some function of the concentrations, times minus delta HR. So let's look at this for 1 second. So here I have on the left side of the equation, I have the system. And you can also see it from here. D theta dt obviously has to do with what's coming in and what's coming out. What's coming in is bringing heat into the system, but this theta is taking heat out of the system. So it's again self-regulatory, because when y was on the other side of the equation, when y dt was when y was big, it came in to decrease dy dt. Similarly here, when theta is big, it comes in with a negative and it tries to decrease d theta dt. Similarly here, when theta is big, it comes in with a negative sign, it tries to decrease d theta dt. So these two terms are self-regulatory. But what happens here is this term is not self-regulatory. So what's going on the other side? Here I have forcing functions. These are forcing. I've got stuff, hot fluid coming in, and I've got possibly the fluid here that will impart heat. So these are both forcing functions. But I have another one from the reaction. And notice that as theta goes up, whereas when theta goes up, these two terms make d theta dt go down, because if they were on the other side of the equation, they came with the negative. As theta goes up, the rate constant goes up, the rate of reaction goes up, and I produce more heat. So this is the opposite of self-regulatory, it's self-enhancing. And what can happen when it's self-enhancing? So I'm not going to solve this in great detail, but if it's self-enhancing, if this term is still small, if it's small, then the system can still reach a steady state. On the other hand, if this thing is big, if this is small, it produces heat when more heat when theta goes up. But these two terms can still take care of it. These two terms can still take care of it, and I can still reach a steady state. On the other hand, if this term gets very big, and it can easily grow big because it grows exponentially, then I can have situations, and again, I'm not going to solve it in great detail, where the system will oscillate. So what does that mean? That means if I introduce a step change in theta in, or a step change in theta C in, then, so if the system was operating at steady state, and I do a step change in the forcing, if I do that, in the old systems, we expected if we start with a step change in the input, at least in self-regulatory systems, we get a step change in the output at steady state. And we don't get a step, we get a steady state eventually in the output. If this term is small, we expect that should still happen. But what is possible is sometimes, if this is too big, then a step change in the input could lead to an oscillatory behavior in the output. So that's something we haven't come across yet. What we found is step change in the input gives me a change in the output that reaches steady state. We found an oscillatory input gives me an oscillatory output. What's interesting about this system is a step change in the input, if this is big enough, can give us an oscillatory output. What is that? Where does that come from? That step change in the input could change the roots of the denominator. Remember, the denominator comes from the left side. But this also has theta in it. So this would also contribute on the left side of the equation because it has a theta in it. Remember, we want to isolate all the theta stuff on the left side of the equation. So that's going to change what I have here, which is going to enter the denominator of f tilde of s. And it's going to change the denominator in such a way that it changes its roots, and it's possible that will give me complex roots instead of real roots. So in a case like this, you can have a step change in the input that gives you oscillatory behavior in the output. That is certainly allowed. And that comes up in industry on occasion. And this was analyzed the first time in great detail in the 50s by Aris and Amundsen. And Amundsen was the advisor of Professor Akrivos, who's an emeritus professor here. And Aris was the advisor of another emeritus professor, Professor Dent. So we have connections there. Are there any questions on that? I know I didn't solve the mathematics in great detail. If people are interested, we can do that in recitation.
So this G function, is this a part of the rate of reaction, and is that a function of theta?
Is the G function, okay. So G is the transfer function. F typically is y prime. So y prime is G times x prime tilde, G times x prime tilde. So typically when I'm doing this, I'm trying to solve for the output, y prime tilde. So G, remember, is y prime tilde over x prime tilde. So in there, so I have to set y in this case is theta, and x might be theta in or theta c in, be either one of those. So if I'm trying to solve for y prime tilde, so I'm trying to solve for theta prime tilde, then notice that there's going to be an s theta prime tilde here, a theta here, a theta tilde here, a theta prime tilde here, and there's also going to be a theta prime tilde coming from here. So all this is going to come to the other side of the equation here. The reason I didn't go through it in detail is because this is already nonlinear, it's an exponential. But theta prime tilde will contribute to d tilde of s, and to the, because it comes from the left side of the equation, so from G, so remember, when this is on the left side of the equation, all this contributes to d tilde, that's all part of G. And then I'm going to multiply explicitly by x prime tilde, which could be either a change in theta in or theta c in. So yes, it contributes to G. But it contributes to y prime tilde via G prime. And the x prime, it gets multiplied by x prime tilde, which will come from one of these, one or both of these. Does that answer your question? Other questions? Okay, so with that, we can now start looking at series structures. So far we've looked at either a first order system or a second order system. Now let's look at series structures. Now, we've looked at series structures a little bit before when we did block diagrams. We looked at CSTRs in series. So we're going to start doing that, just essentially repeating that, just with this notation. So in this case, I'm going to have TI. So this is going to be first order systems in series. So I have TI dyi dt plus yi is equal to kpi x prime tilde x prime. So this would be, I guess, y1. Well, actually, we can do it this way. We can let this be x prime be the same thing as y0. And that way, I don't need separate notation. So what do we have here? We have from that g prime, g of s, which I already did that. That's equal to kp gi of s is kpi, by the same algebra that I did here, over 1 plus sti. That's exactly the same algebra, and going from here to here, all I did was I stuck i's on it. So here, this is I is equal to 1 to dot 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 in systems in series. And remember, this is equal to yi plus 1 over yi. So if I'm interested in yn, that's equal to yn prime tilde over yn minus 1 prime tilde. Yn minus 1 prime tilde over yn minus 2 prime tilde. y2 prime tilde over y1 prime tilde. Times times y1 prime tilde over y0 prime tilde times y0 prime tilde. In other words, this is equal to g n tilde, gn minus 1 tilde, dot dot dot, g2 tilde, g1 times y0 prime tilde. In other words, the overall g overall, for n first-order systems in series, you can think of this as n CSTRs in series, is equal to the product, which is equal to yn prime tilde over y0 prime tilde. It's just equal to the product on I equals 1 to n of gi tilde s. Lots of writing for something that's kind of trivial. We did this before. But again, what we find is because yi plus 1 prime tilde, which is gi, which is this times yi prime tilde. So why don't I just note that yi plus 1 prime tilde is equal to kpi over 1 plus sti yi prime tilde. Notice yi plus 1 prime tilde only depends on yi prime tilde. It doesn't depend on yi plus 2 prime tilde. So you can think of it this way. G1, G2, G3, Gn, that the information is flowing in one direction. That is, to calculate G2, I only need to know G1. I only need to know what came out of G1. I don't need to know what comes out here. Because yi plus 1, this guy, only depends on what comes to the left of it and not what comes to the right of it. And because of that, we call this non-interacting. They're non-interacting because information flows only from left to right. Things would be different if, in order to calculate y3, I needed to know y4 as well as y2. But here for y3, I only need y2. So I only need stuff to the left. And then we have something nice here. This just becomes the product, I equals 1 to n, of kpi over 1 plus sti. So what does that mean? That tells me that, for example, kp total is just the product I equals 1 to n of kpi. I'll just multiply the kpi's out. And the amplitude ratio total, which is g tilde total of I omega Well, it's just the product of 1 over STIs, each one of which gives me this. So I've got the product, I equals 1 to n, of 1 over the square root of 1 plus omega squared tau I, ti squared. Just the product of those. Because each one of these, when I plug in S as I omega and take the magnitude, gives me one of these. And I just take the product of them to get the whole thing. So, well, you might say, okay, that's a lot of writing. What good is that? What can we do with that? Well, let's notice a couple of things here. Anything else I want to say about that? Well, let's look at this. Let's see what's going on here. So we have that y prime tilde is equal to g prime tilde g prime tilde g tilde of s times x prime tilde. So let's look at this. So this is g tilde. And what we're looking at now is n first-order systems in series. Let's see what happens when we look at n first-order systems in series. And I want to do something, a little thought experiment. If I have n first-order systems in series, let's imagine that when n is equal to 1, it's 1 CSTR with a space-time of tau. When n is 2, why don't I make it 2 CSTRs, each one has a space-time of a half tau. So the total tau is the same. When I have 3, I make each one the space-time of tau over 3. So in this case, if I have n first-order systems in series, I want each one having t over n. 1/n the time constant. So the total time constant is the same. If there's no reaction, t is the same as tau. And let's see what happens then. So I have y prime tilde is equal to x prime tilde. Well, if x is a scalar, times this g tilde. So the g tilde is the product of the KPIs times 1 plus s tau over n. But if they're all the same, so they're all identical, then this is just equal to kp overall delta x over s times 1 plus 1 over 1 plus s tau over n raised to the nth power. Or if you like, I can just put the nth power in the denominator. Now, from high school, let's see if you remember as n goes to infinity, what is 1 plus something over n to the n? So let's recall 1 plus a over n to the n as n goes to infinity. Do you remember, anyone remember this from high school? No? As n gets bigger, this gets smaller, but I have more of them. Come on, this is literally high school material. What is the limit of 1 plus, well, let's look at the simple case. What is the limit of 1 plus 1 over n to the n as n goes to infinity? No one remembers. I went to high school long before you did, and I remember this. This is the definition of E, of the basis of the natural logarithm, E. And this is e to the a. So this thing becomes e to the st. And e to the st in the denominator means I have a kp delta x over s e to the minus st. Have you ever seen e to the minus st before? What is, where do you get, this is the limit of the g. So that told me that G tilde of S, as n goes to infinity, was Kp e to the minus st. Have we ever seen e to the minus st before? Remember what we said last time? Your job as students is to come to class ready to learn. Ready to learn means you looked at your previous notes. If you looked at your previous notes before coming to class, you would know the answer to this question. It is unsatisfactory to come to class not prepared to learn. Where did we see e to the minus st before?
For the class transform, so you transform it. When you transform a function into a class transform.
When I transform what?
A function into a class transform.
Which function? Okay, this is not satisfactory that people did not look at their notes. If you like, if this happens again, we will have a quiz at the beginning of every class about what we did in previous classes. Do you want a quiz every class? And then if you come late, you get a 0. How many people want to have a quiz every class? Okay, well if you don't, then you come to class prepared. Otherwise, we will have a quiz every class. Okay, we saw this in plug flow reactor. This was the Laplace transform of a delay. And a delay is if I have a plug with no reaction. It is unsatisfactory, absolutely unsatisfactory that nobody can answer that. Again, next time when I ask a question about what we did in previous class, if no one can answer it, we will immediately have a quiz. Is that clear? Immediately, we will be a pop quiz instantly because it shows you're not interested in learning the material. If you're not interested in learning the material, you'll get a quiz that lowers your grade. Is that clear? I'm sorry I have to treat you like second graders, but I asked you to come to class prepared, and no one came to class prepared. So that means you're saying, please treat me like a second grader. Please. Okay, since you said please, I'll do it. Okay, we can do this slightly differently, the exact same derivation. Notice here, I made all of the reactors identical. They actually don't even have to be identical. What you could do, slightly more general. The same thing, but slightly more general. You can assume that I have T1, T2, Tn. They could be different, but I want to take the limit, but I want the sum I equals 1 to n of the ti's that always equal t. And I want to take the limit where the maximum of t1 tn is going to 0. So I want the maximum of those to go to 0. Such that the sum of the ti's is equal to t. So if I do that, then I'm making this slightly weaker. I don't require them all to be identical. They're getting smaller, but maybe at different rates. And I can still get the same thing, the same answer. Because I can look at the log of y prime tilde. And that's equal to the log of delta x over s plus, and I put the kp in here as well. And then I have plus, or minus, because the denominator, the sum of logs of 1 plus sti. I equals 1 to n. So what I'm doing is I'm taking exactly this expression, but instead of this being t over n, they're ti's. And if I take the log on the left, I get the log of this thing. And the log of the product is the sum of the logs. And it's minus because it's in the denominator. And then instead of this being to the n, I have a sum of ti's. So log of 1 plus s, the ti. Now, since I'm taking the limit where the maximum of these is going to 0, eventually sti is small compared with 1. So in the limit at the max of the TIs is going to be 0, STI eventually becomes small compared with 1. And we know that the log of 1 plus epsilon is equal to epsilon plus epsilon squared over 2 plus dot dot dot. That's the Taylor series expansion for log of 1 plus epsilon. So if I just keep the first term, I have the log of y prime tilde is log of delta x kp over s minus the sum I equals 1 to n. Instead of the log of 1 plus STI, I have the sum of the STIs. Well, the sum of the STIs is just equal to t. In which case, y prime tilde goes to, in this limit, delta x kp over s e to the minus s. So again, I get a Laplace transform for delay, and it's like a plug flow reactor. So whether I have n identical CSTRs in series, that they're all getting smaller at the same rate, or they're all getting smaller at different rates, they're not the same, the total T remains the same, I still get that n CSTRs in series looks like a plug flow reactor. Any questions on that? Okay, another quantity that, that is useful there is I can look at this guy at the amplitude ratio. And let's look at the amplitude ratio. And oh, actually, why don't we plot some things before I actually do that? So let's look at the case where when n is equal to 1. And here I'm going to plot y prime tilde versus, well, we'll see what we plotted it against in a second. So let's look when n is equal to 1. When n is equal to 1, then I have y prime tilde is equal to kp delta x over s 1 over 1 plus s. So here I've just plugged in n is equal to 1 here. From our sheets, what is the y prime? What is y prime of t? How do we invert this? So let's just assume that kp delta x, let this be equal to 1, just to make life easier. And what do we get when we look at our sheet? Yes? What is the inverse of that? What line in the table?
5. 5.
Line 5, although I asked somebody else. So I have 1 minus e to the minus t over 2. So that says if I plot versus t, it looks like this. Well, how about if I have a plug flow reactor? If I have a plug flow reactor, then I have e to the minus st. And when we know that y prime is just a delay. We know that y prime is just a delay. So if this is t over tau, and this is 1, t over big T, then we know for a plug flow reactor, so this is n is equal to 1. For a plug flow reactor, when t is less than t, then nothing comes out. We don't know anything about the change. But when t is greater than t, like this. It's just 0 or 1. What does that mean? I have a plug flow reactor. I do a step change in the input. The output looks the same until tau seconds have passed by, and then the output also has the step. So it's 0 here, and then it's 1 there. So let's do the plug. Plug. N equal 1. And if I go through and I look at some others, then I should make this a little forward. Stronger, nicer. This is the situation as n goes up. So we start out with the n is equal to 1, and why don't I do the n is equal to 1 in orange? And as n goes up, the shape changes and it starts to look more and more like a plug flow reactor. So here we have y prime versus t over big T. Yep.
So when n equals to 1 is in the CSTR score? So when n equals to 1, it's in CSTR?
Is 1 CSTR. N is equal to 2 or 2 CSTRs in series. N is equal to 5 is 5 CSTRs in series. The plug flow is n goes to infinity. But there, what we're doing is we're keeping the total T constant. Or n goes to infinity. Okay? Any other questions on that? Okay, so let's look at the amplitude ratio. The amplitude ratio as n goes to infinity. So let's look at the log of the amplitude ratio. And that's equal to the log of this, which is the sum. So here I actually left out the KP. So it's the log of KP minus the sum, because the product becomes the sum. And it's minus plus it's in the denominator. And here I'm going to look at a case where tau I, Ti is big T over n. So maybe I should back up a step and just not read out steps. So here I have the amplitude ratio is Kp divided by 1 plus omega squared T over n squared raised to the n over 2. Raised to the n over 2, it's 1/2 because it's square root, and there are n factors, so it's the n over 2. So now if I look at the log of the amplitude ratio, that's the log of Kp minus n over 2 times the log of 1 plus omega squared T squared over n squared. Now as n goes to infinity, when n gets large, then I can use this expansion. So when n gets large, then eventually omega squared T squared over n squared gets small, because compared with 1. In which case, this goes to log Kp minus n over 2 times omega squared T squared over n squared. So what does that look like? Well, notice that I can write this as log of Kp minus n over 2 times e to the log omega squared T squared over n squared, or 2 omega T over n. And why do I write that? I write that because now I can plot the log of the amplitude ratio, and this is Kp, versus omega log omega T over n. So if this is my variable, then I have an exponential to that, e to that, with a minus sign. So I have a system that eventually looks like this. The upside down exponential is for n big. And for smaller values, it looks more like this. So I should make the n big a different color so you can see which one's which. And for smaller values of n, it looks more like this. So this is the direction of n going up. And I want you to notice that if I were dealing with the plug flow reactor, remember the amplitude ratio is the magnitude of G of I tilde of I omega. G tilde of I omega for the plug, G tilde of I omega is equal to the magnitude, so I've got delta x Kp over S. What is this? G tilde. So for the plug flow reactor, I have e to the minus I omega t. And I have to take the magnitude. Okay, so it's G tilde, so I don't need the delta x, just Kp. This is just Kp times the magnitude of e to the minus I omega t. Well, the magnitude is the cosine squared minus plus the sine squared. What's the cosine squared plus the sine squared? 1. So this is just equal to Kp, or the magnitude of Kp, because Kp could be negative. So notice that for the plug, I just get this. So again, I have agreement here that this is just, as n goes to infinity, this gets flatter and flatter, and takes more and more, and starts agreeing with that. Are there any questions on that? Questions?
Was this for first order reaction,
This is a first order system. So it's either no reaction or a first order reaction, or a linearized version of a higher order reaction. Because, again, we assume that the first order system looks like this. So this particular term, this y, comes from the outflow and from a first order reaction. And that's why I got the t, where I got the t. First order or an effective or linearized first order reaction. Once I have something that's nonlinear, then it's nonlinear, so I can't use the same machinery unless I linearize. Other questions? Okay, so what we've been looking at so far are series structures, but that were non-interacting. Let's change that to the interacting. And we can think of an interacting system in the following way. So I can think of a bunch of tanks with different levels of them. And I have, so this might be y1, this height y2, this height y3, etc. And I might have an inflow of x. So if I want to write out dy1 dt. Well, dy1 dt, and let's just get my notation correct. I'll just h1 is some sort of height. dy1 dt, well, what's coming in is x. And then I also have, I can write this with a plus or a minus, let's write it with a minus. So k1 times y1 minus y2. So if this is higher than y2, then the hydrostatics is going to push stuff from here to here. Now, of course, if this is higher, then y1 minus y2 will be negative, and it'll go the other way. So K has all that rho GH, that rho G delta H. And similarly, if I go for any of the others, I have HI for I different from 1. dyi dt is equal to ki yi minus 1 minus yi. So that's going in, and going out is k, and I may want to call this I minus 1. This is ki minus 1. And this is ki times yi minus yi plus 1. And let's just make sure I have my eyes in the right place. Yes. Okay, so what does this say? It says that how does y2 change? y2 changes if y1 is bigger than y2. So then I've got y1 minus y2 here, going in. And if y2 is bigger than y3, then I've got y2 minus y3 going out. And the k's have the rho g delta, the rho g's. The k's just the rho g's. But here I'm writing the k's to be different from each other. Is that clear what I'm writing? Is that clear? Okay, so let's do the algebra. So if I rewrite this, I have h1 dy1, and these are all going to be prime variables. h1 dy1 dt plus, so I want to bring all the y1s to the other side of the equation, plus k1 y1 is equal to x prime plus k1 y2 prime. And if I rewrite this, I'm going to let T1 be equal to H1 over K1. So then I have S H1 Y1 prime tilde plus, plus K1 Y1 prime tilde is equal to X prime tilde plus K1 Y2 prime. And now I'm going to divide both sides by H1. And I have S plus 1 over T1 Y prime tilde is equal to X prime tilde over H1 plus 1 over T1 Y2 prime tilde over T1. And this we know is 1 plus ST1 over T1 so when I multiply through, I have y prime tilde, and this is y1, is equal to 1 over 1 plus st1 times t1 over h1. t1 over h1 is 1 over k1 plus y2 prime tilde. Again, I multiplied by T1. So T1 over H1 is 1 of this. Did that algebra at lightning speed, but hopefully that's not too complicated. And then let's do the same algebra here. And here I'm going to let Ti be equal to, where am I? And let's do this for 2. So I'll do this H2. H2 dy2 prime dt is equal to k1 y1 prime minus y2 prime minus k2 y2 prime minus y3. So I want to do it specifically. And I want you to notice that unlike the non-interacting systems, when the information flows from left to right, so to get the output here, I only need to look to its left. Here, to get y2, I need to know y3 and y1. So now and here I'm also going to let t2 be equal to h2 over k2. So here I have h2 dy2 prime dt plus k1 y2 prime plus k2 y2 prime is equal to k1 y1 prime plus k2 y3 prime. And now I'm going to plus transform. So I've got S, so I'm going to have a y2 prime tilde. And now I'm going to have an S times H2 plus K1 plus K2 is equal to K1 Y1 prime tilde plus K2 Y3 prime tilde. And now, again, in order to get T's, I'm going to divide through by K2. So here I have y2 prime tilde times s t2 h2 over k2 plus k1 over k2 plus 1 is equal to k1 over k2 y1 prime tilde plus y3 prime tilde. So I have 1 plus s t2. And now I divide this out, and I have a y2 prime tilde is equal to k1 over k2 y1 prime tilde plus y3 prime tilde divided by 1 plus k1 over k2 plus st2. Well, that would be nice, but right now I want to plug in for y1 prime tilde. So I'm going to plug in for y1 prime tilde what I have here. So let's see what I get. So this says y2 prime tilde is equal to, well, this comes along for the ride, 1 plus k1 over k2 plus st2. And now I want this to come along for the ride also, 1 plus st. And that's multiplied by, well, I've got k1 over k2 times y1 prime tilde. That gives me x prime tilde over k1 plus k1 over k2 times y2 prime tilde plus y3. Now that didn't have a 1 over 1 plus st1, so I got to put that in. And now I can cancel these k's. But I notice that there's a y2 here that I have to move to the other side of the equation. So I have to move it to the other side of the equation. So I have y2 prime tilde times, let's move this to the other side of the equation. So if I move it to the other side of the equation, I have 1 minus k1 over k2 divided by these two guys here, which I didn't bother rewriting, is equal to those two guys in the denominator, these two, times x prime tilde over k2 plus y3 prime tilde times 1 plus st1. And now what I need to do is I need to, again, I need to solve for y2 prime tilde. All right, so let's figure out what 1 minus this thing is. So I've got those two guys, and I'm going to have to continue here because I'm running out of backward space and this monstrosity is in the way. So I've got, let's multiply these two out. So I've got 1 plus k1 over k2 plus st2, that's all times 1, plus st1 times that, plus st1 plus st1 k1 over k2 plus s squared k1 k2. So I just multiply these two out. And I'm going to subtract off k1 over k2. If I subtract off k1 over k2, I just get that, because I subtracted it off. So I have y2 prime tilde times this. And now I've got this denominator here and here, so I can cancel the denominators. It's just equal to x prime tilde over k2 plus y3 prime tilde times 1 plus st1. So what did I do? Let's just show you exactly what I did in the algebra. In order to bring the 1 in here, I wrote this as this denominator over itself. And then I subtract, then everything, all the terms had the same denominator, so I got rid of the denominators. And then I just had that thing minus k1 over k2. Got rid of the denominators, and I'm just left with the numerator. So as a result, I have y3 prime tilde is equal to, it's equal to x prime tilde over k2 plus y3 prime tilde. All of that times 1 plus s, so divided by, let's see, this denominator. So the denominator is 1 plus s times t1 plus t2 plus k1 over t1 k1 over k2. plus S squared T1, T2. Divide, and that's all underneath that. Let's see if there's anything else I'd like to say about that before going on. No. Okay, so now notice that 1 plus ST1 is not a factor of this because I canceled the K1 over K2. So the denominator is the same for both. The numerator has a 1 over K2 or 1 plus ST1. Those are the numerators. And it's the denominators that give me the stability. So we have a quadratic equation here. And let's look at what the root of the quadratic is. S 1 and 2 is equal to minus B, T1 plus T2 plus T1 K1 over K2. Plus or minus the square root of that thing squared. Minus 4AC, 4AC, 4T1, T2, over 2A. And let's just notice what the discriminant is. So the discriminant is the square of that parenthesis. Let's write out the square of that parenthesis. That's T1 plus T2 squared, plus T1 K1 over K2 squared, plus 2 T1 K1 over K2, T1 plus T2. So I just have this A plus B equal to 3 squared. A squared plus B squared plus 2AB. Minus 4T1 T2. Now, T1 plus T2 squared is T1 squared plus T2 squared minus 2T1 T2. When I add 4T1 T2, I get T1 squared, when I subtract 4T1 T2, I get T1 squared plus T2 squared minus 2T1 T2. So this is equal to T1 minus T2 squared plus T1 K1 over K2 squared plus 2T1 K1 over K2 T1 plus T2. So immediately we can see the following. This is all inside the square root. This is a perfect square, this is a perfect square, and this is something positive because the t's and the k's are positive. So this whole thing is greater than 0. Since it's greater than 0, that says the roots are purely real. Because the discriminant is positive. Moreover, the discriminant, this thing squared, is actually this. And I'm subtracting something. So the magnitude, even though it's positive, the magnitude of the discriminant is smaller than the square of this. So when I take the square root, I get something smaller in magnitude than this. So even when I add it to this is more negative than this is positive. So even this guy with the plus sign is going to be negative. So it's greater than 0 and it's negative. And this one is clearly negative. They're both negative. So as a result, the system, both roots of the denominator are real and negative. If they're real and negative, that means when I get either the S1 or S2t, these are real and negative, these are going to be stable and overdamped. Meaning, they're going to decay exponentially. There's no oscillation. Now we need to do a little bit more on this, but unfortunately, Father Time, or Mother Time, or whoever it is running out on us. So what else do we need to do to figure out here? Well, I guess we'll do a little bit of a spoiler alert instead of actually deriving the solution. But what happens in the spoiler alert? Well, you can notice that since this is a quadratic, I can write this as 1 plus s. I can call these roots, I don't know, let's call these sigma 1 and sigma 2. Sigma 1 times 1 plus s sigma 2. Because it's quadratic, where sigma 1, these are sigma 1 and sigma 2. So this is equal to 1 plus s times sigma 1 plus sigma 2 plus s squared sigma 1 sigma 2. So I can compare this quadratic with this quadratic. Let's compare them. So that tells me sigma 1 sigma 2 is equal to t1 t2. They have to be the same because they're the coefficient of s squared. It's the same quadratic. But sigma 1 plus sigma 2 is equal to t1 plus t2 plus something, thus t1 k1 over k2. So what does that tell me? That tells me that t1 and t2 are the basic time constants for each of these. They're these guys, the basic time constants. And those would be the time constants if they were non-interacting. What you can see here is the product of the roots is the same as the product of the time constants, but the sum is bigger. The sum of the sigmas is bigger. I want you to think of the following situation. Let's say I'm looking at 16. I could have 4 times 4 is 16. I could have 2 times 8 is 16. And I could have 1 times 16 is 16. A little example. In both cases, the product gives me 16. But notice, the further apart these two numbers are, the bigger the sum. These two sum to 8. These sum to 10. These sum to 17. So what does that tell me? That tells me that sigma 1, sigma 2 are further apart than t1 and t2. T1 and T2 would be the time constants for the non-interacting system. Here, sigma 1 and sigma 2 are further apart. That is, the bigger of sigma 1, sigma 2 is bigger than T1 and T2, and the smaller is smaller than T1 and T2. So what does that tell me? That says I have one exponential decay that's really fast, and another one that takes its time. Meaning, the interacting system is more sluggish than the non-interacting system. It's slower. You could also show that sigma 1 minus sigma 2 is bigger than T1 minus T2. And that would, again, 4 minus 4 is 0, 8 minus 2 is 6, 16 minus 1 is 5. So again, that tells me that the sigmas are further down on this table than the t's. So the interacting systems are more sluggish than the non-interacting systems. We'll continue with this next time, but I'm happy to answer questions.
I think you solved for, on the top line on the right, you solved for y2, not y3?
Yes, y2. Thank you. My mistake. That's what happens when I don't look at things. I just make mistakes. But luckily I didn't make a mistake here. This seems to be right. Are there questions? So again, the basics is the interacting systems are quite different from the non-interacting. In the non-interacting system, the time constants are just all the time constants in the individual systems. In the interacting situation, the time constants are the s's, the sigmas, not the t's. So, and the sigmas have a faster and a slower one. They're more sluggish than the non-interacting system. Question? Okay, so again, for next time, and for every class, you look at your notes before class, and you come to class prepared to learn. Coming to class prepared to learn means you've looked at your notes, and you either ask me questions about what you didn't understand, or if you don't ask me questions, then you're ready for me to ask you questions.